Okay, so this is a uh, overview of the spring 2021 midterm solution. And I'm going to skip all of the exam rules, etc. And I'm also going to assume that you have a copy of the midterm in front of you. I'll make a PDF also that you can look at. So here we have the start of the game, or the start of the exam. We have a question called Flipper, or a game called Flipper. Flipper is a simple game. We've got the 7 contiguous spaces, and this is how the board starts. We have a G for the goal at the bottom, and you have 2 moves for your piece. You can either you can flip. Oops, let's not do that. You can flip your piece to change direction, and you can take a step to go forward 1 square. And then I give a bunch of examples of games you win if you get your marker to the goal, and you can't move above the top space or below the bottom one, so there's no wraparound or anything. And you just keep playing till you win. There's no losers. So I give a few different examples. You can, of course, play badly and get into an infinite loop. So here's the first question. Let me try and line that up a bit better in here, which is, what size is the state space for the flipper game? What's the smallest number of states you need to fully represent flipper as a state space search problem? And you actually had to justify your answer. Okay, so let's think about this game. The game has 3, 4, 5, 6. Did I give it 7? 1, 2, 3, 4, 5, 6, 7 squares. And in each of these squares, your game piece can be pointing up or pointing down, right? So effectively, if you think about it, we could imagine that we have 1 state for each of the cases where the arrow is pointing up in that state, 1 state for each of the cases where the arrow is pointing down in that state. Is there 6 or 7 here? 1, 2, 3, 4, 5, 6. There would be another one. 7, right? So we need sort of a state for each of the arrows pointing up and the arrows pointing down, right? So you know, if you were imagining this, right, this might be state 1 with the arrow up, and this is state 1 with the arrow down, and this is state 2 with the arrow up, right, representing the second space, and state 2 with the arrow down, and so on. The only thing is, so that would give us 14, right? 7 times 2. If I could actually draw 14 of these, right? The only difference actually is when you get to the goal, right? Because if you think about it for a minute, the game ends as soon as you get to the goal. So you really don't need 2 states for the goal. You only need 1. There's 2 ways to think about this. One is that you're always going to arrive at the goal facing downwards, and then the game is over. And the other is you can actually just sort of ignore that fact and say, well, as soon as I get to the goal, the game is over. So it doesn't really matter how I represent, you know, I don't need to represent the goal as 2 different things, because once I'm there, the game is over, done. So we can just represent that as one thing. But so I was looking for some sort of an explanation like this. You know, the actual words that I was sort of expecting from someone would be something like, you know, there are 7 positions, and or 7 spaces, whatever, right? There's 7 spaces, and the game piece, oops, that says piece. Fortunately, you guys are typing, can be in any of them facing, let's see, so a little bit more room here, facing up or down. And most people said so. That would be 7 times 2, but don't need goal space facing up, since you can never get there. That would have gotten you full credit. Well, if you then said, here, let me scroll a little bit. So 7 times 2 minus 1 is 13. So that would have gotten you full credit. And the other way to have explained this for full credit could have been, you could have said the same kind of argument, except you say there's 6 normal spaces where you can be up or down. Pen's a bit big, isn't it? There we go. For up or down. So that's 6 times 2 plus 1 goal space. And so we have 6 times 2 plus 1 is 13. So that's what I was looking for. Let's just look at these other quick ones on the left here. True or false, if the player uses depth first search without multipath pruning to select a path in this game, it's possible that the search might never find a winning solution. That's true. You may just do back and forth if it like this game. It's possible. It's not definite that that's going to happen, but it's possible. If you use breadth first search without MPP, however, you will always get a solution because you will look at paths in length order, right? We didn't talk about any cost to the paths other, we didn't say there was any distinction between the costs of the different moves, flip versus move. Here, player uses lowest cost first. Is it possible that it is possible that the search might never find a winning solution? Again, the answer is no, it's not possible for lowest cost first search because you're looking at the at your path length again, and because we haven't specified anything about how we're computing cost except for the number of moves, and so that is also false. If you use depth first search with multipath pruning, then it's not possible that the search might never find a winning solution. So now we've got a false for this one as well, right? And breadth first search with MPP is no worse than breadth first search without MPP. So again, this is false. And lowest cost first search with MPP, again, with MPP is no better than without MPP. So the answer is we will always find a winning solution in finite amount of time, right? It's not that breadth first search and lowest cost first search are always identical searches when you use MPP versus not. In this particular problem, they probably are. And regardless, if without MPP you can find a path, then for sure with MPP you can find a path. Okay. Okay, so let's talk about this next game, Flipper Plus Plus. Flipper Plus Plus is exactly the same as regular old Flipper, except that now the game starts with the marker in any space facing up or down. And in particular, the goal is still in the bottom space. So if the marker starts in the bottom space, the player instantly wins and the game is over. So I give you another number of possible scenarios that might happen, including the player just starts in the goal. So this is very, very much like the, here's the question. Let's see if I can get that actually in the picture frame. I suppose it's sort of almost there. What size is the state space for the flipper game, right? What is the smallest number of states that you need to represent that? So 2-01, good, we're here. What have we got? We have the 7 states, right? Right, so is that 7 or is that 6 again? That's 6. So there's my 7 states. And what we said before was we had 7 states times 2 possible orientations for the player. The player could be facing up or the player could be facing down. And then we took away one of those states because we said, well, before the goal was in the bottom state and you could never start in the goal state. So you always had to approach the goal from above, which meant that you always sort of ended up in the goal um, facing down. Now you can, in fact, start in the goal facing up or down, right? So, the number 14, right, where you just say times 2 is completely justifiable. To say there's 14 different states, the state where you're starting, you know, what your orientation is, up and also down, and you're in that state. Since starting in the goal state is a winning state, you could, in fact, think about answering this as 13 because if you represent my players in the goal state, and the player is facing up or down, it doesn't really matter here, right? So you could say 13, but you could also say 14 here, fully justified. Now, the flipper coin challenge is in fact super tricky. And so I was pretty generous with the grading of this problem, but let's take a look at this for a second. So just like in Flipper++, the player's marker can start in any space, even the goal. I moved the goal to the 5th space from the top. That's no big deal, right? It's just somewhere. But now we've got 2 coins. The coins can't start in the same space where the marker is, and they can't start in the same space as the goal. And they can't be in the same space. As soon as the player moves into the space with the coin, the player automatically picks up the coin, and you can't put the coin down when you've picked it up. The game ends and the player wins when the player has both coins and moved to the goal space. All right. So to think about this problem, let's start by thinking about a slightly easier problem. Let's think about a problem where we have the goal in a fixed location to start out the game every time the goal is always in the same location, and also every time each of the coins starts in the same location. So the only thing that's varying is where does the player start. If you think about this from the player's perspective, and we're just thinking about what sort of state information, what sort of information do we need to keep in an individual state, right? There it might have arrows between states or whatever. The information that we need to know when we are in a state, right, is which of the locations it is, right? So there's 7 of those locations. And we need to multiply that by 2 because the player may be facing upwards or downwards, just like before. And then we also need to multiply that by the number of different coins the player might have with them. Of course, since the player, when they arrive in a space, they automatically pick up the coin, we don't really have to differentiate between whether there's a coin in here or not. We just say, well, I'm here and I have a coin, right? Because if there's a coin in there, I've picked it up. So I could be here and have 0 coins. I could be here and have 1 coin. I could be here and have 2 coins. So that's a total of 3 different possible options, right? So that would give me 7 times 2 times 3, right? So that's 6 times 7, which equals 42. That was for the coins are sort of, that was one game where the coins were pre-placed, right? Now 42 is actually a little bit higher. We can cut that down a little bit because we can say, all right, when you are in the final goal state, let me scroll this just a little bit. Again, if you have 2 coins and you are at the goal, it doesn't matter whether you have 2 coins and you're facing upwards or 2 coins and facing downwards. You could still have the winning location. So we could take away 1 space for the goal state, right? We could sort of merge 2. Can you see that? No, you can't see that. We could merge 2 of the goal states together, right? The goal state where you have 2 coins and you're facing up, and the goal state where you have 2 coins and facing down. Those could merge into a single state. All right. Other tricks that we can do, let me move over to reduce. So that would mean we would have 41 states, right? And then other tricks that we can do to reduce this a little bit is we could say, well, you know, for each of the spaces that we were thinking about, you can have 0, 0 or 1 or 2 coins, right? But there are, in fact, 2 locations where you can't have 0 coins, right? The locations where those coins are pre-placed, you cannot have 0 coins in there, right? Because the coin is there. So if we're thinking about, remember we're thinking about that we have a spot with an orientation and how many coins we have, either 0 or 1 or 2. There's going to be 4 locations. Or sorry, 2 locations where the arrow is pointing up and there's already a coin there, so you instantly pick it up, or the arrow is pointing down and there's already a coin there and you instantly pick it up. All right, so that's 2 states, plus 2 more states where the other coin is, right? Where we've sort of accounted for by multiplying, by saying it's, here, let me write it out again, by saying it is 7 times the 2, where that is the, so where the 2 is the up or down, and the times 3 where the 3, excuse me, where the 3 is the 0, 1, or 2 coins, right? We've actually got 4 spaces or 4 states which can never happen. You are upwards in, let's say your coin is in, one of your coins is in state 2, you're upwards in state 2, you're downwards in state 2, you always have 1 or 2 coins in there. You can never have 0 because the coin started there. Similarly for if the coin started in state 7, right? So that's that. So we can, in fact, take this original number of 42, subtract 1 off because the goal being in the goal with 2 coins merges those 2 states. You can collapse them into 1. And we can also remove the 4 states that we could never get to. So that gives us a grand total of 37 states. Now, if this had been the problem, it wasn't, we'll talk about that in a minute, and you had said 42, you would have gotten 99% of the credit, because thinking about the you know, the goal, maybe not 99, 95, something, you would have done fine. You still did fine. Thinking about the that the goal actually collapses one of those states and that the 0 coins collapses, that's you know, that's getting pretty subtle. The hardest part of this problem is just figuring out this 7 times 2 times 3, right? Except that, in fact, the problem is harder than that, because the problem, let me move up a little bit so you can see this bit, right? So we were down to 37. Or maybe, you know, maybe you got 42, fine. But that was 42 different states. Do I have 7 here? 1, 2, 3, 4, 5, 6. Why do I always draw 6? 42 different states when, I don't remember where I put it, but you know, the goal is here and the coins are here, right? But what happens if the coins don't start there, right? The coins could start in a bunch of different places. In fact, the coins, if we think about it, the coins can start in any of the 6 places where the goal isn't, right? The goal was always fixed. We said the goal was fixed in there. And we just need to pick 2 of these remaining spots for the goal to, or for the coins to start, because of course the player, we said the player can't start in the same place as the coins, but that just means when we are looking at our state diagram for where things are happening, right? We've got the states that represent whatever they represent. We'll just say some of them can't be start states, right? So if we are in the situation where the coins are there, then these 2 locations can't be start states, right? Anyway, so the question is, how many different ways are there to figure out where you can put 2 coins? And we're effectively trying to put take 6 spaces and choose 2 of them for coins, right? So that's 6 choose 2, which you may or may not have seen in discrete math. So I didn't, if you explained what you were thinking about in this and went beyond the basic 42 or 37, I started giving you more points. That was where or really we were, it was only a point and a half, I think, that I took off if you didn't get this far. So 6 choose 2 is 15. And so that means there's 15 different ways to pick any 2 of these free squares. And so really the number of states that we want is 15 times that 37 we have up here, which equals 15 times 37 equals 555. Yuck, right? And if you'd said 15 times 42, you would have gotten almost all the credit, because you already got almost all the credit for saying 42, right? So I didn't take off much if you missed this part. This part was sort of the extra harder part, and what I was really looking for was your ability to think about how many states there were in here. Okay, so let's look at this question. Suppose that the cost of each move in flipper coin challenge is always 1, and you decide you want to use A* search to win at this, and you come up with this heuristic here, where the heuristic of a particular state is the distance between the player's location and the farthest coin's location if the player is not holding both coins, or just the distance between the player and the goal otherwise, right? And then I just explain what distance is, right? And your friend says, wait, don't we need an admissible heuristic? And you say, yeah, but this is admissible. And then the goal of the problem is to explain how you know that this is an admissible heuristic. So, there's 2 parts to this problem. The first is you just need to be able to define what is admissible, right? So an admissible heuristic, a heuristic by itself, right, takes a node and returns a non-negative number, right? So it has to be non-negative, right? And it also has to be less than or equal to the actual cost of the lowest cost path from the node to the goal. And the trick here is to recognize that your goal is not just say picking up a coin, right? But your goal, right, you're only at the goal state when you have picked up both coins and brought them back to that state that is labeled G in the problem. So let's see if I could actually draw 7 spaces here now. 5, 6, is that 7? 1, 2, 3, 4, 5, 6. Look, I got 7. Right, so I think the goal is in that space, right? And so let's just think about it for a minute, right? Let's just look at what's going on here, and then we will write an answer, okay? So if my player is here, 1, 2, 3, and 1, 2. So if my player is here and doesn't have any coins yet, right? Then the value of the heuristic is going to be 3, right? And 3 is actually already more than the number of steps even to get to the coin, because I have to do a flip, right? But more importantly, 3 is by absolutely less steps. It's less than or equal to the number of steps, the cost of getting to a coin, picking it up, getting to the other coin, picking it up, and then bringing both of those coins to the goal, right? Because that's what tells us if it's admissible or not, right? So in this answer, in this problem, I was actually looking for you to give me kind of, I was looking for 3 things, right? The first is just to define admissible. Right. The second was to make it clear that you understand what the cost to the goal is versus the cost that's defined in in this function here, right? The cost. So you need to talk about what is the cost, the actual cost to the goal versus the heuristic, right? And so essentially, if you said something like, if, let's see, if the player hasn't picked up, oh, you can't read this, can you? Let's scroll a little bit down. All right. So, oops. So if the player hasn't picked up at least one, no, that's not what I want to say. If the player still hasn't picked up so let's talk about the actual cost versus to the goal versus the heuristic. To do that, we need to think about both of the possible cases for the heuristic. Either the player is not holding both coins or the player is holding both coins, right? So if the player is not holding both coins, then the actual cost to goal is cost to pick up both, and then, well, maybe, and then add to that the cost of getting to the goal state. Let's scroll a bit more. Let's see, where can I put the answer here? Let's scooch it over. So what do we got? If the player is not holding both coins, then the actual cost to the goal is the cost to pick up both and then add that to the cost of getting to the goal state, right? Let's say to pick up one or both. So that's the actual cost, right? But the heuristic of that state is just the cost to get to one coin. So that's definitely less than the cost to get to coin and then to goal. Right? So that's if you don't have the if you don't have both coins. And let's just slide over. Is just going to let us slide over a little bit more? Yeah, there we go. If you do already have both coins, then the cost is either distance plus 1 if you have to flip, or just distance. heuristic of S equals the distance, I should say distance to goal, right, from player. If you said this without all these extra little bits, it would be fine. But is either distance from player to goal plus 1, or if you have to flip, or just distance. Now the heuristic itself is exactly equal to the distance, and distance, so h of s is less than or equal to the actual cost. Okay. This is way more than I actually required of people to write out, I think. But again, you had to give me some indication. And of course, I also didn't write out the definition up here of, right? I didn't write the definition of admissible because you can do that, right? Pretty much most people got that right. There were a couple of people who totally got that wrong, but defining an admissible heuristic, right? That's really what I'm saying here. Heuristic. The point is you have to argue somehow what the actual cost is to the goal versus what the heuristic says it is. And the heuristic has two parts, so you better cover those two parts. So next question, if the true or false, if the player uses A* search without multipath pruning, using the heuristic described above to select a path in this game, it's possible that the search might never find a winning solution. And the answer is no, because we know, so that's false, right? We know that A* without MPP, right? A* without MPP with an admissible heuristic is guaranteed to find a winning solution, right? An admissible heuristic does not guarantee that you will get an optimal solution, right? To have an optimal winning solution, you actually need to have a consistent heuristic, right? But if you look at the if you look at this heuristic at all, you'll see that it's pretty straightforward to see that it's not only an admissible heuristic, but it is also an optimal. Sorry, it's also a consistent heuristic, which means that A* with this heuristic will indeed find an optimal winning solution. So therefore, it's not possible that the search might never find, right? So this is false. Okay, so this last part is the monster challenge. And it says on each turn, the player makes a move, and then the monster randomly selects a move of its own. And you lose if you're ever in the same space as the monster, or if the monster moves in the player's space. And otherwise, the player wins if it picks up 2 coins and gets to the goal, as long as the monster wasn't in the goal when the player got there. So you set up with the normal flipper coin challenge, and then the monster goes somewhere. And I said the player now has one move we haven't seen before. Player moves are the player can flip, right? Can step just like before, but they can also jump forward 2 squares, ignoring any coins or monsters in the intermediate square. And I'm going to assume you have this whole thing, but I will also point out that, oh, well, so I say, for example, in the game on the right, the player is initially in space 7 with 0 coins, and we're going to write that as 7 facing up 0, right? 7 facing up holding 0 coins, 7U0. And the player can flip down, so that would be 7D0 because they're facing down, or they can move 1 step and automatically pick up a coin, so that would be P move up 1 step to 6 and pick up a coin. So now they are 6 facing up with 1 coin, or they can jump to space 5, missing out on the coin on space 6, right? So that would be jump to 5. So in the space 5, U is facing up and 0 is the number of coins they have. And then the monster actually has 2 moves here, right? It can go up 1 square, or it can teleport to square 7. So in this case, if the monster's in square 3, it could go to square 2, so then it's in square 2, or it could teleport to 7, so it could be in 7, and so we have either the monster in 2 or monster in 7. And then I ask you to draw an outline of a game tree corresponding to the first turn, and I say the player moves and then the monster makes its random move of this game for the configuration shown above. So I mean for this particular picture, right, which I also copied to the slide, and fill in the P and the M parts. And then on the leaf nodes, I said, here's your evaluation function, fill out the evaluation function, and then label the internal node with the expect-to-max value. All right, so here is, I pasted it somewhere. Here we go. Here is a copy of my solution. And let me just talk you through a few features of this thing. So the first thing that I expect you to do was to draw a max node at the very top, right? And if you look at this, of course, the player, if you look in the picture over here, the player starts in row 7 facing up with 0 coins, and I actually gave you this in the assignment too, right? But so the player, so I expect you to draw a triangle because it's a max node. We start with a max node, 7U0, and the monster is at 3. And initially you don't know these values yet, so you don't know these values yet, right? But now the player takes a move, the player is max, and the player has 3 choices of moves, right? But the player, this is an expect-to-max tree because I said the monster is going to make a random move. So therefore, I expect these guys to be circles, right? Because even on here, I said that the choice nodes are a circle, right? And you'd had this, you know, a lot of this stuff, including the definition of the shapes before the exam. Anyway, so you draw 3 circles because the player can move 3 different places, right? Where can the player move? Well, the player can flip upside down. That corresponds to the 7D0. The player can move up by 1 space, which also picks up a coin. So that's space 6 facing upwards with 1 coin. Or you could move, you could do that jump and so end up in space 5 facing upwards, but with no coins, right? And now it's time for the monster to move. And if you notice, the monster starts out in space 3 in all of these because that's where the monster was before it makes a move. And now the monster is going to make its random move from the choice node, right? And in each time, there's only 2 places the monster can go. It can either go to location 2 or location 7. So you'll see that up here, this 7D0 gets carried down to there, and the monster is either in 2 or 7. And this 6U1 gets carried down to here, but now the monster is in either 2 or 7, and so on. So we have that for everything. So so this was sort of the outline that I expected you to start with, right? You had to draw this picture. And then once you had this picture, the next step was to take a look at this evaluation function and compute for each of these spaces the values, right? And if you look, and so we're trying to compute it, right, just for the leaf nodes right now, right? Which I drew as squares because I'd said to draw them as squares in the minimax picture, but I'll take them as max nodes because they are also sort of max nodes. Sorry, I said minimax, I meant expect-to-max. Anyway, but so if you look at these, this particular node here, the monster is in space 7 and the player is in space 7, so that's going to be a negative 25. The rest of them you need to actually figure out the values. So for example, let's just go through it really quickly. It's 4 times the number of coins picked up. So in this guy, we have 0 coins, right? So it'll just be 0 for that, minus the absolute value of the monster's location minus the player's location. So it's basically the distance between them. So the distance between 7 and 2 is 5, but so that turns out to be 0 minus 5 is the value, right? Distance between, oh, well, this one we already filled out with the value of 25 because that was that one. When we look at this one, we say, oh, this one actually does have a coin, right? The player picked up a coin for this one. So that starts us with 4 times number of coins picked. So that is going to be 4 minus something in each case here. And in this left one, it's going to be 4 minus Oh, look, well, 4, because the distance between the player and the monster is 4, so that ends up just as 0. And in this one on the right, it's 4 minus, the distance is 1. Oops. So that turns out to be the value 3. And then for the one on the far right, again, these guys have 0 coins, so it's just going to be 0 minus something, right, because I'm using these equations. And of course, the player and the monster are not in the same spaces in either of these, so I know I'm not using that negative 25 or 25 thing. So it's just negative of the distance between them. So this first one works out as negative 3, and the second one works out as negative 2. Okay, so that was step 2 of this. And then the last thing, well, the almost last thing that you needed to do, you need to propagate that back upwards. So you need to say, this is an expect a max node, which means that, and since I said at random, we figure it's going to be 50-50, so you just need to take the average of these two. So negative 5 plus negative 25 is negative 30, and that divided by 2 is negative 15, so we get a value of negative 15 for this one. We have 0 and 3 here, so we propagate that one up, we get 1.5, and we have negative 3 and negative 2 here, so that adds up to negative 5, which gives us a value of negative 2.5. And now to figure out this guy's value, well, that's a max node, right? So max node actually gets to pick. So max looks, and it says this one has a value of negative 15. This one has a value of 1.5. This one has a value of negative 2.5. I'm going to take the biggest one. I'm going to take the 1.5 because that gives me my highest expected value. And so we end up with this beautiful picture. Okay, so we're going to do an alpha beta prune of this, or sorry, a minimax search using alpha beta pruning of this tree. And just to remind you, here is the alpha beta implementation, right? For the purposes of this explanation, instead of initializing v to negative infinity, I'm going to initialize it to negative 1,000, which is pretty close to negative infinity given the values that we have. And positive infinity, I'll use 1,000. So so I'm going to just kind of step you through this. So notice here, I've got the alpha as negative 1,000, the beta is 1,000, and the v starts as negative 1,000 because this is a max node. You'll also see as I step through this demo that I've got little numbers to just show you where we visited and in what order. So I'm going to do this relatively quickly because you, of course, have a copy of this algorithm and you can look at it and see what's going on and take a look at each of the mins and maxes as we go. So I'm just going to kind of step through this and not say a whole lot, except remember that these numbers that are in here are just the order that I'm visiting the nodes, just so that we can keep track. So for example, this is the 6th node we visited, but the 6 doesn't have anything to do with anything. It is, however, a terminal node. We've already visited the 7, so notice V was 7, but we're going to pass this up to max, so we kind of expected that 10. Look at that, V and alpha are now 10. We're going to pass V back up. So beta gets reset to 10 because this is a min node, and we keep stepping along. And notice that we've passed this alpha and beta down to here now. So we keep going. Life is all very good. We are step 10 of our algorithm, but 12 is our actual value of the leaf node, which we will pass back up. And that 12 is going to change our V, but now we notice that we have a max node where the V is greater than or equal to beta, so we don't actually have to go any further. We're just going to return this V, and we prune that first leaf down there. So let's pass that up. So we've got the 12 we passed back up here. And of course, since this was a min node, we ignored the 12, right? Because we're trying to take the minimum of the values from the children. This 12, not that 12. This 12 in here is just, this is the 12th node we're going to visit, because in a minute I'm going to make that turn into a 13. Look at that. Okay. So now alpha up here at the root is 10 because we know that, well, mostly because the algorithm told us that, right? But effectively, that tells us that we could get a 10 with what we've searched so far. We want to keep searching. So we go down to the next child and we propagate the alpha and the beta here. So beta is still 1,000. really beta should be positive infinity, and alpha is 10. And so we keep kind of trucking along. We get this 1, which we pass back up. And so now in this max node, V is 1. V is not greater than beta, so we look at the 9. There we go. We pass it back up. Now we've readjusted V to be 9, which we will pass up. There we go. We've passed this V of 9 up here. Now look, alpha is 10, V is 9. We have a min node, and the min node says if V is less than or equal to alpha, return V, and V is indeed less than or equal to alpha. So we're just going to return V without exploring this stuff. So these nodes, this whole subtree gets pruned, right? So we propagate our V back up. And Max decides that it doesn't like that 9 very much. It would much prefer the 10 that we have on the left. So we take another step, and we take another step, and we take another step, and we pass that 5 back up, and we have a Max node, and 5 is not greater or equal to beta, so we keep going, and we have a 4, and so we're going to take that 5, keep that 5 to pass it back up, and we pass the 5 back up. Notice that this is a min node, and this 5 is indeed less than or equal to this alpha of 10. The reason we prune is because the algorithm tells us to prune, right? Because V less than or equal to alpha, return V. But if you're thinking about why does it make sense to prune, it makes sense to prune because we know we can get a 10 already from somewhere. And this is a min node that could pick to go this way and get a 5. So why the heck would it? This is going to be 5 or worse, which is not as good as 10 for the max. So we take our last step, and we are up here, and we know that we can get 10. So in terms of future questions, it looks like, let's see, we have the 3 is pruned, the 11 and 2 are pruned, and the 6 and 8. So 3, 11, 2, 6, 8. So let's just look at our problem here. We had to, the first question was, what's the value that Max expects to get? And if you look at the tree we were looking at a minute ago, the value is 10 because 10 is what we got propagated up here. And so the value that Max expects to get is 10. Can I write that somewhere? Where's my little guy? Come on. Dum-da-dum-da-dum. I know this is so exciting, but I know also that you guys like to see answers in boxes. So 10. Wow. Very exciting. And the next is, which leaves are never looked at because they're pruned or their ancestors are pruned? And we said that 3 was never looked at. Can I scroll this just a little bit more? I'm not doing a very good job here. Oh yeah, there you go. The 3 is in there. So, so 3 is not looked at, and neither is 11 or 2, we said. And also, we said, now I don't remember, I need to look. We said 6 and 8, yes. So we'll cross off 8 and 6. And is there one more question? No, there's no more questions. Okay, so there you go. Fabulous.